Myself Dr. Rashmi Saxena, and I am working in Government MH College of Home Science and Science, Jabalpur. In this lecture, we will discuss about complex spin-spin interaction in first order spectrum. In my previous lecture, number 5, I have discussed about the theory of spin-spin coupling between A and neighboring X proton. Suppose proton A is showing absorption and its neighbor is X proton. So due to the presence of X proton, the signal of A will split up into two peaks and the intensity of the peaks will be 1:1. Second type of spin coupling between A and neighboring two X protons, that is the AX2 spectrum. In this, we have discussed that the signal of HA proton will split up into three peaks and the intensity of the peaks will be 1:2:1. In my previous lecture, I have also discussed the spin coupling between proton A and its neighboring 3x protons, that is AX3 spectrum. Here, due to the spin coupling, the signal of proton A will show 4 peaks and the intensity of the peaks will be 1:3:3:1. So we can arrive at a rule that is known as the N+1 rule. So if we wish to find the multiplicity of the signal from a group of protons, then we have to count the number of protons on the neighboring carbon atom. That is, suppose it is N, then we will add 1 to it and it will give the multiplicity of the signal. Let us discuss spin-spin coupling in detail. There are two nuclei A and X, and their spin is represented by alpha, that is the up spin, and beta, that is the down spin. Because of their spin combination, 4 energy levels are created, which are represented by alpha alpha, alpha beta, beta alpha, and beta beta. Now suppose the two nuclei A and X, they do not couple. So the energy separation between alpha alpha and alpha beta, this represents the transition for nuclei X, that is spin of X nuclei is changed here. So this is the resonance energy for X. Similarly, another energy separation between beta alpha and beta beta also shows the resonance energy of X. The two resonance energies for X are identical. Therefore, X nuclei shows the absorption once and there will be a singlet for X nuclei. See, similar thing for nuclei A. Energy separation between alpha alpha and beta alpha. This is the transition for nuclei A. Spin of nucleus A is changed here. So this corresponds to the resonance energy of nuclei A. Another energy separation between alpha beta and beta beta. This also shows the resonance energy of A. The two resonance energy of A are identical. Therefore, it will resonate once and there will be a singlet for nuclei A. Now consider nucleus A and X, they couple with each other. Because of the coupling, the energy levels are changed. Energy level alpha alpha and beta beta, these two energy levels get destabilized by energy of J/4. And energy level alpha beta and beta alpha gets stabilized by energy J/4. Now see what happens to the resonance energy of X. One resonance energy of X, that is from alpha alpha to alpha beta, is lowered by J/2 energy, whereas another resonance energy for X is from beta alpha to beta beta is increased by J by 2. So there will be two resonance energies for nucleus X. Therefore, the nuclei X will show the resonance 2 times and its signal will split up into 2 peaks. And since the energy is decreased here by J by 2, and in the second energy separation, that is the beta alpha and beta beta, energy is increased by J by 2. So the gap between, the spacing between the two peaks will be J. Half J plus half J will be a J, that is the coupling constant. Similarly, we can explain for nuclei A also. The resonance energy for nucleus A here from alpha alpha to beta alpha is lowered by half J, and another resonance energy for nuclei A, that is alpha beta to beta beta, is increased by half J. Therefore, nucleus A also will show the resonance 2 times and its signal will split up into 2 peaks, and the distance between the 2 peaks will be J, because first resonance energy is lowered by half J and another resonance energy is increased by half J. Half J plus half J is equal to J. So in this manner we can explain the coupling between two neighboring protons. In NMR, protons are designated by different alphabets. Chemically equivalent protons are represented by same letter, and protons for which the chemical shift is quite different, they are designated by X, Y, and Z. For protons for which the chemical shift is very close, they are represented by A, B, C. Then protons, those who have intermediate chemical shift, are designated by M and O. And the first order spectra is represented by where the chemical shift difference is quite large as compared to the coupling constant. It is said that the chemical shift is greater than or equal to 6J, then the spectrum will be first order spectrum. Observe this NMR spectrum. This is the NMR spectrum of an ester for which the molecular formula is C4H8O2. There are 3 signals indicating presence of 3 non-equivalent protons. One signal which is present at 1.2 ppm value, it is given by 3 equivalent proton, which is indicated by the integral value, and this is a triplet. Another signal which is seen at 2 ppm value is given by 3 equivalent protons, and it is a singlet. Third signal which is seen at 4.1 ppm value is a quadrate and given by 2 equivalent protons. These 2 equivalent protons are d-shielded protons. Therefore, we can imagine that these methylene protons must be close to oxygen. And the presence of a singlet, which is given by 3 equivalent protons, indicates presence of a methyl group close to which no proton is present. So this methyl group must have been close to carbonyl group. And the presence of triplet and a quadrate represents the ethyl group. So this is the NMR spectrum of a compound ethyl acetate. Now you can see here that methylene protons are d-shielded protons because it is present to oxygen, which is highly electronegative. So methylene protons are d-shielded protons. Methyl protons are slightly d-shielded because of the anisotropic effect of carbonyl group. So in this manner, we can interpret the NMR spectrum. This is the NMR spectrum of isopropyl benzene. There are 3 signals. One signal which is present at 1.2 ppm value, it is a doublet and it is given by 6 equivalent proton. Another signal which is present at 3 ppm value, it is a septate, and one signal which is present at 7.2 ppm value, it is given by 5 equivalent proton. This area 7.2 and between 8, this represents the presence of benzylic proton, and there are 5 benzylic protons. And 6 equivalent proton shows the presence of 2 methyl groups. And there is one methane proton which has got 2 neighbors. So there are 6 protons. 6 plus 1 is equal to 7. Therefore, the signal of methane proton will show 7 peaks. It will be a septate. Similarly, neighbor of 6 equivalent methyl proton is a methane proton. And due to this, the signal of methyl proton will split up into 2 peaks. It will be a doublet. The intensity of peak is 1:1. Similarly here, the inner peaks are longer than the outer peaks. Therefore, this is the distortion because of the coupling. This is the NMR spectrum of 2-bromobutanoic acid. From the structure, we can expect 4 signals for 2-bromopropanoic acid. One signal because of the acidic proton. We know that the acidic protons are highly de-shielded protons. So the signal for the acidic proton is seen out of the scale at 11 ppm value. For your convenience, this peak is inserted in the chart. Another signal is because of the methane proton. Methane proton will be de-shielded protons because of the presence of bromine. So it is seen at the downfield. So the signal from the methane proton is seen at 4.1 ppm value, and signal from methylene proton is seen at 2 delta value, and the signal from the methyl proton is seen at 1 ppm value. Now look at the multiplicity of methyl proton. The signal for the methyl proton is split up into 3 peaks. It is a triplet. This triplet indicates that in the neighbor there must have been 2 protons. So the neighbor of methyl proton is the methylene proton. Now coming to the signal of methane proton. Signal of methane proton splits up into 3 peaks. It is also a triplet. So presence of triplet also indicates that the neighbor of methane proton is a 2 protons. So this is the methane proton and the neighbor is 2 methylene proton, and because of this the signal of methane proton shows a triplet, and it is de-shielded because of the presence of bromine atom. Because of the electronegativity of bromine, it will, from the minus I effect, it will withdraw the electrons, and therefore the electron density on methane proton will decrease and the proton will be de-shielded here. Look at the multiplicity of methylene proton. It is a quintet. There you can see 5 peaks. This shows that the methylene proton has got 2 neighbors. One is the methyl proton, 3 equivalent protons, and another neighbor is methane proton. So there are 4 neighboring protons. So the signal splits up into 5 peaks. That is, a quintet is seen for methylene protons. So in this manner we can interpret the NMR spectrum of 2-bromobutanoic acid. This is the NMR spectrum of an ester for which the molecular formula is C7H14O2. In ester, alpha protons, alpha with respect to the carbonyl group, are de-shielded because of the anisotropic effect of carbonyl group, and the signal is seen close to 2.1 to 2.5 ppm value. Another protons which are close to singly bonded oxygen are much de-shielded, and the signal is seen at delta 3.5 to 4.8 ppm value. So this is the NMR spectrum for which the molecular formula is C7H14O2. This molecular formula represents 3 isomeric esters, and we have to establish the structure of ester on the basis of this NMR spectrum. So in the spectrum, you can see integral values which are given below the signals, and we can calculate the number of protons which are giving a particular signal. So from the integral values, we can calculate that signal A is given by 6 equivalent protons, signal D is given by 3 equivalent protons, signal B is given by single proton, signal E is given by 2 equivalent protons, and signal C is given by 2 equivalent protons. These 2 equivalent protons are highly d-shielded protons, and the signal is seen close to 4. It means these 2 methylene protons must have been close to singly bonded oxygen. Now look at the triplet and quadruplet combination in the spectrum. This triplet and quadruplet combination indicates the presence of ethyl group. Now look at the doublet, which is given by 6 equivalent protons. 6 equivalent protons means 2 methyl groups, and it is a doublet. It means close to these 6 equivalent protons there is 1 proton, and a septate from 1 proton indicates that neighbor of this single proton must have been 6 protons, and 6 protons are 2 methyl groups. So on the basis of this NMR spectrum, we can establish that this is the NMR spectrum of isobutyl propanoate. Now look at the structure of isobutyl propanoate. And this is the ethyl group. Ethyl group means a combination of triplet and a quadruplet. Signal of methylene proton will be a quadruplet, and the signal from methyl will be a triplet. So this is quadruplet triplet combination, shows the presence of ethyl group. Now these 2 methylene protons B, which are close to singly bonded oxygen, are d-shielded proton, and the signal is seen at close to 4 ppm value. And this is the isopropyl group. Isopropyl group, 6 equivalent methyl protons and 1 methane proton neighbor. So the signal of 6 equivalent protons shows a doublet, and the signal of methane proton shows a septate because of the presence of 6 equivalent protons. So in this manner, from the NMR spectrum, we have established that the compound is isobutyl propanoate. This is the NMR spectrum of a compound for which the molecular formula is C7H14O2. And there are 3 signals. Below the signals, integral values are provided from which we can calculate the number of protons giving a particular signal. So signal A is given by 9 equivalent proton, signal B is given by 3 equivalent proton, and signal C is given by 2 equivalent protons. Signal A, it is a singlet, and it is given by 9 equivalent proton. It means there are 3 methyl groups are present, and close to 3 methyl groups there is no proton is present. Therefore it is a singlet, that is, it is a tertiary butyl group. Combination of triplet and quadruplet indicates presence of ethyl group. So this compound must have been tertiary butyl propanate. You can see the structure of tertiary butyl propanate. These are the 3 methyl groups of tertiary butyl group which are giving a singlet here because there is no proton is present on the neighboring atom, and ethyl group CH3CH2 it gives us triplet and a quadruplet. So this NMR spectrum represents the compound tertiary butyl propanate. This is the third NMR spectrum of the series, in which the molecular formula of the compound is C7H14O2. And we have to establish the structure of ester on the basis of this NMR spectrum. There are 6 signals, and below each signal, integral values are given, from which we can calculate the number of protons providing each signal. So, signal A is given by 3 equivalent proton, signal F is given by 3 equivalent proton, signal E is given by 2 equivalent protons, signal D is given by 2 equivalent proton, signal B is given by 2 equivalent proton, and signal C is also given by 2 equivalent protons. These 2 protons, methylene protons, are d-shielded protons, and the signal is seen at 4.1 ppm value. It means to say that these 2 methylene protons are present close to singly bonded oxygen atom. That's why they are d-shielded proton. Now observe the signal A and signal B. Signal A is a triplet, and the intensity of the peak is 1:2:1, and the inner peak is slightly longer than the outer peak. Similarly, observe the signal B, in which the multiplicity, it is a quadrate, and the intensity of the peak should be 1:3:3:1, but the inner peak is slightly longer than the outer peak. Draw arrow on this signal and draw a arrow on this signal A. Now they are pointing to each other. It means to say that the 3 equivalent proton which are providing signal A are coupling with the 2 equivalent proton which are giving signal B. So this quadrate and the triplet combination indicates the presence of ethyl group. And other 2 methylene protons, this methylene proton and 3 equivalent methyl proton here, they constitute N-butyl group. So this ester must have been N-butyl propanoate. You see the structure of N-butyl propanate. This is N-butyl propanate. So this is the ethyl group, which is giving a signal A and signal B, and these 2 methylene protons which are giving signal C are d-shielded because they are present close to singly bonded oxygen, and because of the de-shielding effect of electronegative oxygen, the protons are de-shielded and the signal is seen at 4.1 ppm value. And the signal from the D, it has got 2 neighbors. 2 methylene groups are present, so it will be a pentate. D signal will be a pentate. So D, it is a pentate. You can count the number of peaks here. Signal from the E methylene protons, the neighbor are methyl and the methylene. 3 plus 2, 5. The 5 neighboring protons plus 1, it will be a sextate. So a sextate is seen for the protons E. So in this manner we can interpret the spectrum and we can elucidate the structure of ester. So we have seen that molecular formula is identical, C7H14O2, but there are 3 different isomeric esters, and we can establish the structure of all the 3 isomeric esters on the basis of their NMR spectrum. This is the NMR spectrum of a compound for which the molecular formula is C10H14. The integral values indicate the number of protons giving a signal. So a signal E, which is present at 7.2 ppm value, is given by 5 equivalent proton. And this is the area where the benzylic proton shows the absorption. It means there is a benzene ring is present in the compound. So we have accounted for 5 protons, equivalent proton, and remaining 9 protons give these 4 signals. So one signal A is given by 3 equivalent proton, signal B is given by 2 equivalent proton, signal C is given by 2 equivalent proton, and signal D is given by 2 equivalent proton. Signal A, it is a triplet, B is a sextate, C is a quintet, and D again it is a triplet. So the splitting pattern indicates that N-butyl group is present. So this compound must have been 1-phenyl butane. You can see the structure of 1-phenyl butane. So the 5 equivalent protons which are providing signal E, this methylene group which is a triplet is seen as signal D, and quintet, this methylene group which is giving a signal C, sextate, methylene, these are the methylene protons which are giving sextate. Here it is signal B and the triplet of the methyl proton. This is the NMR spectrum of a compound for which the molecular formula is C10H14. So we have to establish the structure of isomeric compound on the basis of this NMR spectrum. The integral values indicate that the signal A is given by 3 equivalent proton, signal D is given by 3 equivalent proton, signal B is given by 2 equivalent proton, signal C is given by a single proton, and signal E is given by 5 equivalent proton. So these 5 equivalent protons are benzylic proton as they are showing the absorption in a down field close to 7.2 ppm value. Now signal A, it is a triplet, signal D, it is a doublet, signal B, it is a quintet, and signal C, it is a sextate. From the multiplicity of the signal, we can establish that the compound is 2-phenyl butane. This is the structure of 2-phenyl butane, and we can correlate the structure with the signals. Now these are the 5 equivalent proton which are giving this E signal. Signal A is given by this methyl proton which is a triplet. Signal D is given by this methyl proton which is a doublet. This methene proton which gives a signal C which is a sextate because it has got 2 neighboring groups. At one there are 3 methyl protons are present. At another carbon there are 2 protons are present. So in all there are 5 neighboring proton. So the signal of methene proton is splits up into 6 peaks. Similarly, this methylene protons here gives a signal B and the quintet is seen. Quintet means 5 peaks are there. So it must have been having a 4 neighboring proton. So 3 methyl protons plus 1 methene proton. So there are 4 neighbors. The signal of this methylene proton splits up into 5 peaks and a quintet is seen. So in this manner we can establish that this is the NMR spectrum of 2-phenyl butane. This is the NMR spectrum of furan 2 aldehyde and this is the example of Amx spectrum. Amx spectrum is seen in unsaturated or aromatic compounds. In furan 2 aldehyde there are 4 signals. One signal is because of aldehydic proton which is highly de-shielded proton and the signal is seen in the downfield at 9.7 ppm value. It is de-shielded because of the anisotropic effect of the carbonyl group. Other 3 protons are designated as A, M and X protons and therefore there are 3 different groups of protons are present. Proton A shows a signal close to 7.7 ppm value. Proton M shows a signal close to 7.3 ppm value, and proton X shows a signal close to 6.6 ppm value. And here you can see long range coupling, that is the J4 coupling, is also present. That is, the proton A couples with its neighboring proton HX, and it also couples with proton M. Similarly, proton M couples with its neighbor proton HX, and for the J4 coupling, it also couples with proton A. And the proton X has got two neighbors. It couples with proton A as well as proton M. So the three signals which are given by proton A, X and M, they are double doublets. These are the three double doublets given by proton A, M and X. Proton A shows two splitting. It couples with proton X and the signal is splits up into two peaks, two lines are seen. Again it couples with proton M, so every line is splits up into two peaks. So a double doublet is seen, that is, four lines are seen in the signal of proton A. So there are two types of coupling, JAX, which is a J3 coupling, and JAM, which is a J4 coupling. Similarly, proton M couples with proton X and it gives two lines, and again it couples with proton A, so the two lines are further split up into two peaks. So in all, a double doublet is seen. Here also there are two types of coupling constants, JMX, which is a J3 coupling, and JAM, which is a J4 coupling. Proton X also couples with proton A and it gives two lines, and again it couples with proton M and it is splits up into four lines. So there are also two coupling constant, JAX and JMX. The magnitude of JAX, which is a J3 coupling, and JMX, it is also a J3 coupling. The magnitude of the two coupling are different. Therefore, in each signal, we get double doublet.